So my name is Iikka Virkkunen and the topic is NDT reliability and probability of detection. Now, the main purpose of NDT is to evaluate a component, usually to see if there are some unacceptable defects there. So we seek to gain more information about the component. For today's presentation, I want to recast this question in terms of lack of uncertainty. Information is exactly the same as lack of uncertainty, and to do NDT is to reduce uncertainty. So why is NDT reliability so important then? Well, because it is the heart of non-destructive testing to reduce uncertainty about the biggest flaw that might be in the component, about the location of the flaws, about what has happened to the component. But if the NDT itself is not reliable, if there is significant uncertainty about the test method itself, NDT is then not able to reduce this uncertainty. There may be cracks missed, or there might be false calls that cause additional repairs or something like this. And in the end, the NDT is not as valuable as we would like it to be. So as a rule of thumb, unreliable non-destructive testing is useless, or it could be much worse. It could give us false sense of security, or it could make us do unnecessary repairs or things like this. So then it follows, okay, reliability is very important. How good is good enough? How reliable does the NDT really need to be? Now, this is a difficult question, and there is not a one-size-fits-all answer to it, obviously. But let's imagine and take a look from different viewpoints. So let's say that we have a very high quality inspection method that has 99% probability of detection, only 1% false call rate, and then we go ahead and we inspect a component. Because of the history, we expect that this component has one crack in every 10,000 inspections. Very rare. This is rather typical that we don't see cracks very often in non-destructive testing. And say that we found an indication. Now, what is the likelihood that this indication is actually a crack? Let's break down the numbers. We do 10,000 inspections. We expect to find one crack. We have 99% detection rate. So with 99% probability, we expect to find that crack. At the same time, we have 1% false call rate. So with 10,000 inspections, we expect to do 100 false calls. So given that we found a single indication, we expect that to be a false call. So even with this very high accuracy and very low false call rate for an inspection like this, when you rarely find any cracks, it doesn't really sound like a good enough even then. Now, if you do the same kind of inspection in a different location where you expect to find cracks in 1 to 10 inspections, then, if you break down the same numbers, you do 10,000 inspections, you expect there to be 1,000 cracks, you expect to find 990 of them, miss 10 cracks, which is bad already. But then you only do the same 100 false calls, so then most of the indications are actually cracks. So it depends on the conditions of the inspection, what is the reliability, but usually when we do NDT, the finding a crack is a very rare encounter. And because of that, the reliability needs to be very high. Now, let's look at this from a different viewpoint. Let's say that for the NDT to be worthwhile, it needs to pay for itself. So we look at it from a monetary perspective. And of course, not all things can be put in monetary value, and this is a simplification, but for argument's sake, let's say that we need to cover the cost of the NDT by the benefit that it brings to us. So in the cost side, we have the cost of doing inspection, which might be significant. We need to develop the system. The people need to come to the location, and it takes time. It also takes time from the production. Then the NDT might be uncertain. We might make some false calls, and these incur some additional cost. And the NDT might be uncertain. It might also leave some misses there. So all of these together are the cost of the system if we do inspection. And then on the other side is the cost of these flaws if we do not do NDT at all. And usually the cost of inspection and cost of false calls are what requires or takes most of the focus, but the cost of the misses that remain there, or the cost of the damage that might be there if we miss a single crack, is the dominating one. So because of that, we mostly do NDT in these high reliability conditions where having a single crack grow and cause damage would be a very significant cost indeed. And because of that, also from the NDT side, the cost of missing a crack is the most significant cost. So we are particularly focused in having a very high probability of detection, very reliable inspection. It also follows that it doesn't pay to look for cracks that are not there. If we can, in some magical way, know that a certain crack cannot be there, it doesn't add any value to inspect it. It also doesn't pay for look for cracks that are known to be there. If we know it already, we don't gain any more information. And it only takes a single crack to kill a mission. So reliability is paramount. Also, if we look at NDT in a wider context, when we do the NDT, we reduce the uncertainty, but where does the benefit come from? Well, the benefit comes from giving these results to the strength analysis people who can say, okay, now I can use this component for 10 more years or 1 more year. And because of that, we also need to have this reliability and our results in the context of the people who actually use it. So for NDT, we talk about cracks and we try to find cracks. And cracks are also important for the strength analysis people. For them to know that the structure is safe, they need to know that there are no cracks bigger than certain size. Other things matter, the crack location, the loadings and things like this. But for the first approximation, the crack size is the most important thing that determines how dangerous the crack is. And if we look at the materials degradation people, the smaller the cracks are in general, the slower they grow. So then we have more time to make some other things with the cracks or compensate with other means. And this is common in many damage mechanisms, whether it's stress corrosion or fatigue or others. The bigger the crack, the more dangerous it is for materials degradation point of view as well. So cracks and crack size in particular act as a combining tool. The NDT reduces uncertainty by showing the strength analysis people what's the biggest flaw that still might remain in the component. And this is something that they can use to allow the use of the component. And this is where the benefit comes from. So not all flaws are created equal. The danger of a crack is primarily dependent on the crack size. Other things also matter, but crack size is a good approximation. Smaller cracks provide more time and are easier to compensate with other means. And that means that non-destructive testing is also always pushed to find smaller and smaller cracks. The smaller cracks we can find, the more value we get out of the NDT. But if there are any big cracks, it's paramount that you find these first. These are the most dangerous ones. And the happy coincidence, or well, at least the coincidence, is that the bigger the crack is, usually the more easy it is for NDT to detect. So the more dangerous cracks are easier for the NDT to detect. So when do we do NDT? Well, when decreasing uncertainty is useful. So there needs to be some uncertainty about the condition that we can decrease. And also the NDT needs to be capable enough to effectively reduce it. And this means that most NDT is done when we look for unlikely cracks that are probably not there, but they could be there. And if they are there, they are dangerous. So it follows that missing a single one could be a disaster. So if you look at the time span of a hypothetical component, usually the failure probability draws a curve like this. So in the x-axis, we have service time. In the y-axis, we have failure probability. This is sometimes called the bathtub curve. It's known throughout various industries. In the early years of the component life, the manufacturing defects dominate. So, just after manufacturing, there might be some defects. When we take the component into use, it breaks down quickly. However, as the component has already serviced some time, these kind of manufacturing defects are no longer there. They've already broken if there are them. So the probability of failure decreases quite rapidly after certain use. Now, there are some random events that could always happen, so it doesn't go to 0, but it goes to low value if the component is well designed. And then as the service time accumulates, we accumulate more and more uncertainty about the current status of the sample. And later in life, the probability of failure increases. And now this is rather different. Because of different loads during the service time or changes in the original conditions that might be indistinguishable in the beginning, but during the loading of the component lifetime they accumulate, the condition of two nominally similar components might be very different. So it's not just that the damage accumulates, it's more importantly that the uncertainty about the state of the component accumulates. So it might be that after 10 years of use, one component still has 10 years life left, and the other one is going to be broken in half a year or 1 year. So then it means that we do NDT into locations, we do manufacturing inspections to make sure that the manufacturing defects do not cause any early life failures. And more importantly, we do service inspections to reduce this uncertainty and make sure that we still have more life. And in many cases, the life of a component can be extended significantly by reducing this uncertainty. So that's basically why NDT in general is so difficult. For all inspections that we make, to make these as efficient as possible, we focus on the more difficult ones. We want to find small cracks, which is difficult. We want to find them when they are probably not there. And this is difficult for humans to do. Look year after year of data and never find anything, but still maintain focus. We need to do this with very high confidence, and not missing even a single crack is paramount. There was once an NDT inspection in a nuclear environment in Germany. And the inspector came back and said, I have an indication. And they asked, well, what do you mean you have an indication? Is it a crack? Is it not a crack? What is it? Well, the problem was that the system was set up using EDM notches. So the only thing that the inspector could reliably say is that it's definitely not an EDM notch in the power plant. But nobody expected to have EDM notches in the power plant in the first place. So this did not reduce uncertainty significantly. There was a lot of discussion, and they decided that, okay, they can run the power plant for another year. But during this year, they need to make sure that they can explain what the indication means. So they went ahead and made cracks to actual components, redid the inspection, compared the indication with the actual cracks, and find out that the inspector was right. It was not a crack. So there never was a crack in the power plant. But the moral of this story is that results in this industry are not very valuable unless they are highly reliable. In fact, they might be counterproductive. They might actually induce a lot of unnecessary work. So that leads to NDT design balance. Smaller cracks are less dangerous. So we want to find small cracks, and we are pushing the NDT methods to find smaller and smaller cracks. But at the same time, the bigger cracks are easier to find. So we are also pushing the NDT towards more and more uncertainty and less reliability. But at the same time, we do need to maintain the very high reliability. So this then leads to what I call the most dangerous question in the industry. What is the smallest flaw you can find? Now, the danger with this question is that it's really a trick question. When you ask an inspector what's the smallest crack that you can find, what he thinks intuitively is the smallest cracks that he has actually seen, what he has actually found. And this is a mistake. Do not do this. If you're doing this, you're setting yourself up for failure, because this is not really what they are asking. Remember, results are not very valuable in this industry unless they are reliable. So what they are really asking is, what is the smallest flaw that you can reliably find? And this is a very different thing. To find out what is the smallest flaw that you can reliably find, you should be thinking about the biggest flaws that you have actually missed. But how do you know, as an inspector, what you have missed? Most people never know what they've missed. And the few inspectors that find out the hard way what they have missed may have difficulty finding employment later on. So this is not an experience that we would want on anybody. So we need to have a better way to assess NDT reliability and find out what we can miss, and by that answer this question. And this is an important question. The structural integrity people need to know what can be reliably found so that they can take full credit for the NDT. Otherwise, the NDT doesn't give the value that it could. So to improve NDT reliability, we first need to be able to measure it. Now, this might be a little simple. 100 years ago, if you can't measure it, you cannot prove it. But measuring NDT reliability is sometimes difficult and sometimes expensive. And there is a temptation to do something that appears to increase reliability, even if we can't really show that it actually did. But the problem with this approach is that some of the things that we do that feel like improving reliability actually do not, and they can actually be counterproductive. They can actually decrease reliability. So you really do need to measure it to be able to improve it. So to answer this question, we need to define it more closely. So what can we find reliably? Now, we also need to define how reliably. The more reliability we want to extract from an NDT method, the more difficult it becomes to show that, more expensive it becomes to show that. And also with this estimate, it isn't worth much unless it's reliable. So the next question is how reliable an estimate you want. The more reliability you want to have on the estimate of the reliability, the more effort you need to make. So there is a reliability confidence trade-off, and unfortunately it is the inspectors that carry the cost. So basically, to show that you can very confidently cross this bar, we need to raise the bar higher and show that you can cross that as well, and then we can have confidence that even if you have a bad day, you still can cross the lower bar as well. And this is where probability of detection comes to play. So probability of detection is a measure of non-destructive reliability. There are other measures, but POD is very established and well, very well justified and good to use. And it also forms a good basis. So even if you end up using some other metric, looking at it from a POD perspective first and then adjusting for the other metric is a good way of thinking about these systems. And the POD is defined as a probability of detecting the crack, given that it is there, it is present, and usually as a function of flaw size. Now, many inspectors say that other things matter as well. I mean, if the flaw is in difficult location, it's more difficult to find and so on. So why only flaw size? Well, the significance of the flaw size is that it functions as a good proxy to discuss with the structural integrity people. They need to know what flaw sizes can be found. They don't care so much about how difficult it is for NDT to do it. And so we need to communicate the results in a way that they can actually take credit for. Now, in some cases, we can take other parameters in there as well, but then we also need to talk to the structural integrity people so that they really fully understand what the results mean. And usually this is not worthwhile, so we just do it with a crack size and everything else is bundled into uncertainty of the estimate. And maybe in NDT 4.0, we can have more accurate estimates and better data. But for now, NDT as a function of flaw sizes is usually the best way to go. So how do we do it? Let's start out with a sort of practical approach so that you get an idea about what all this means. So let's say that we want to find what is the smallest flaw you can reliably find, which is equal to the biggest flaw that you could miss. So we want to find a flaw that you can find at least 90% probability of detection and 95% confidence. Now, this is time-honored tradition to define the smallest flaw that you can reliably find as the flaw that you can find with at least 90% probability of detection and 95% confidence. It's a good trade-off of what we can show and what we can achieve with methods. So let's say that we start out with a ill-defined plan. I give you 10 samples that have cracks. I've mixed them up with all kinds of other samples that do not have cracks, and I say, please inspect them. And you go ahead and you inspect all these 10, and you find all of them. And you come up with the perfect results, and you're very happy with yourself. But unfortunately, I have some bad news for you. It's not good enough. What do you mean not good enough? I found all 10. You said 90% probability of detection. That means that from 10 cracks, I could have missed one and I still have 90% probability of detection. Yes, but the more tricky threshold here is the 95% confidence. You've shown that you could find 10 cracks today, but I need to be confident that you can find 90% day in and day out for the foreseeable future. So because of that, I need to have higher confidence. I need to see more. So how much more? How many flaws do you need to find for me to be confident? If you break down the number, it comes down to 29. So if I mix up 29 cracked samples with the same crack size amongst samples with no cracks, you go ahead and you inspect and you find every single one of them. Then I say, okay, now I'm confident. You've proven that you have at least 90% probability of detection with 95% confidence. Now I'm happy. But of course, to find these 29, you actually have to have better than 90% most of the time. To have a 50% chance of passing this kind of exam, you need to have about 98% POD. And this is the knockdown that we take. But this is problematic. If you miss even a single crack, then we don't have a result. You haven't shown POD for this crack size or any crack size. And this happens sometimes in practice, and this causes problems. So it's not the best way to do POD. Also, the crack size does matter. We are not just interested about can you find this single crack size with sufficient reliability. We are also interested about can you also find, even with a bit less reliability, some smaller cracks that could help. We can take some credit about that. And also we want to know where is the limit, how far we are from the limit. Maybe we can push the requirement a little bit further if you're very good. So we can make some key assumptions to make this easier for us. We say that, okay, because of the setup for NDT and for most NDT methods, we know that bigger cracks are easier to detect. So we can take credit for that knowledge. We also say that POD is a curve with S shapes. So big cracks, easy to find at 100% or close to 100%. Small cracks, impossible to find. And in between, we have some sort of transition. So the better way to estimate POD is to have a range of crack sizes, about 60 or so, preferably more cracks. Some big enough to be easy to find, some small enough to be impossible to find, and most importantly, a lot of cracks in the difficult to find region to say where see where the cracks are. So then we can make this test. You find some, you miss some, and then we can fit an S-shaped curve here, and then we can have a POD curve. So this is what a typical POD curve looks like. In the x-axis, we have flow size, in this case, millimeters. In the y-axis, we have probability of detection. We draw the found cracks on the up here. We have a little bit of variance here just to make them easier to see, but all of these are found. And in down here, we have all the missed cracks. Again, variation for visualization, but they've all been missed. And then we have the best estimate line here, which is the solid curve. And then we have the lower confidence bound in here, and 90% probability of detection at the 95% confidence bound tells us what is the A9095, which is the smallest flaw that we can repeatedly find. So let's look at this curve and let's highlight some key points. So we have the best estimate capability line as the solid line, 95% confidence bounds. We are usually more concerned about the lower confidence bounds. Here are the big flaws that are easy to find. We expect all of them to find. If you miss a big flaw, you're in trouble. Here are the small flaws that are impossible to find. You will miss them. If you don't miss cracks in POD exercise, the exercise is set up poorly. The smallest cracks that you've actually found are here. They're quite small, in this case, about 1.5 millimeters. And as you can see here, people who find the small cracks also miss the big cracks at the same time. So the biggest flaws that you actually missed are here, about 2.7 millimeters, almost twice of the smallest flaws that you actually found. So if you're estimating your capability based on the smallest flaws, you are setting yourself up for failure. But of course, we only had 60 cracks. We need to have this confidence day in and day out for the next years. So we compute the confidence bounds, and then here we have the lower limit confidence bound. And for this case, we have the A9095 at 3.7 millimeters. So more than about 2.5 times the size of the smallest cracks. And after all this work and 60 cracks and all of this, the one number that we take from this is the A9095, the smallest crack you can reliably find, which is usually a bit higher, a bit bigger than the biggest flaws that you actually missed in the exercise. So key takeaway, the A9095 is the industry standard for the smallest cracks you can reliably find. It's usually in an exercise like this a bit larger than the largest flaws that you missed. Sometimes when you have very many flaws, you can actually have it even a little less. Missing small flaws is okay, but if you miss even a single big flaw, the results change drastically. So the small, if you find one small flaw here, it doesn't really make any difference, but even missing a single big flaw here pushes this all the way here, and it makes a problem. So how do we actually do it? It's important to determine the POD at the upper end with high confidence level. So we need a lot of data. usually we always have too few flaws because flaws are expensive traditionally, and we need to have some statistical methodology to make this achievable in the first place. So the early attempts were to have a lot of flaws like this. We have a lot of flaws here, and then just divide the flaw size axis, the x-axis, in bins, and this is called a bin POD or empirical POD. So then we can have a certain number of flaws for every bin, and we can compute the POD for every bin. But this approach has a problem. If you make the bins very wide, then you don't really know too well where the POD lies, and if you make it very narrow, then you have only few flaws within each bin, and then you don't have statistical confidence. So it doesn't really make much use of the flaws, and you need to have way too many flaws to use this approach. It's a good first approximation when you look at this kind of data, just to see where you are. So too few points per bin and bad statistical reliability. So the next thing to do is to apply the 29 rule. And this is called the 29 out of 29. It's used still extensively in the aerospace application, space application. And this is the way to do 90-95 POD with the smallest number of flaws. So if you have 29 flaws with the same crack size, you find them all, and you have shown 90-95 POD for this crack size. If you miss one, you're in trouble. You need to have a lot more cracks, and this is why it has some drawbacks. So there are two better ways to do it, and these are both ASTM standard ways. So the next way is what is called an A hat versus A POD. Now in this approach, we approach the NDT method as a measurement problem. So we say that the NDT measures a signal with continuous amplitude. If you have an NDT method that does not have a signal of this nature, like penetrant test or something like this, then this is not the approach for you, but don't worry, there are better approaches there. But if you have something that has this signal aspect like eddy current, then maybe you can use A hat versus A. And then in addition to the signal, you have noise. And the idea here is that since this is a measurement setup, we can define detection as a signal that has sufficient signal to noise ratio. So as long as the signal is high enough from the noise, we can set up a threshold, and anything above the threshold is called a flaw and is detected, and anything below it is not called a flaw, and if it was a flaw, then it's missed. And the crack or no crack decision is based solely on signal amplitude. So we do not take into account any kind of human factors issues. We do not take out any judgment. If the inspectors can actually find flaws that have very low signal to noise ratio, more power to them, but we can't take any credit for that. And then if we set the threshold lower, then we get more cracks, but then we get more false calls as well, because the noise is now interpreted as flaws. So this is good in a way that we can make POD with few flaws. About 40 flaws are needed to get idea about the variance that we have on the signals, but it's limited in applicability. The inspection method must yield continuous signal. The inspector must rely solely on signal amplitude. They can't use any other effects, and people usually do use other effects. So this is mostly applicable for automated inspections. And also there are some methodological limitations. We need to have A hat versus A, which is linear, and in some methods it's not linear. And so we need to do something, or we cannot use this. And also the scatter is very important. So we need to make sure that the scatter is independent of the crack size. So in a good A hat versus A, we can have a result set like this. So we have the cracks here again. We measure the signal strength, and then we can measure the variance here. And based on the variability here, we can actually estimate the probability of detection, which means the probability that the flaw is higher than the signal threshold that we've given. And then we get a POD curve like this. Now, in A hat versus A, the error bounds are related to scatter in A hat versus A correlation. It's very efficient in terms of crack use. But if you have smaller crack sizes, you might get overly optimistic results. Also, you could have a perfectly good inspection that has non-linear relationship. This is a real inspection result. The inspector marked their signal amplitudes, and they are strikingly non-linear. It did not cause any trouble for the inspector. He still found all the flaws. But for this methodology, now the results are unusable. So it's a good tool to design automated systems, also now used for model-assisted POD to assess the effect or likely effect of flaw orientation or other easily simulated aspects into expected reliability, but it misses many effects inherent in the manual inspection, so it's not applicable in every case. The other method that is more applicable is the hit-miss POD. So in this time, we don't really see the signals as such. We give the samples to the inspector. We ask the inspector, what is your judgment? And based on the flaws that the inspector found or did not find, we assess the POD. So this now takes into account at least some of these human factor issues that people are sometimes inconsistent. It can be used for inspection methods where there are no signal amplitudes like penetrance or this, things like this. We do make some strong assumptions to make it easier for us. We assume that the POD is a functional form, usually logic function. We assume that the POD goes all the way from 0 to 100%. We also need to set up the system so that we have at least 20% of hits or 20% of misses. So you do need to miss cracks to have a POD curve. And we need to have a clearly defined transition. If these conditions are not fulfilled, then we need to think about how we set up the exercise and repeat it sometimes. And the error bounds are typically a bit larger than A hat versus A because we cannot make use of the signal amplitude information. So the hit-miss POD looks something like this. In the high end, we have the found cracks. Here we have the missed cracks, and then we fit the best estimate line, and then we can compute the confidence bounds, and then we can extract the A9095. Now, the error bounds here are because these 60 cracks are a sample. And you know, when you do the inspections day in and day out, your performance may vary, and we need to have more confidence. And because of that, we compute the confidence intervals. And there is a caveat to this. Sometimes it's tempting to bundle together results from many different inspectors, but the different inspectors might actually have different POD curves. And if you do this, then the confidence bounds describe an average inspector. And then if you pick one actual inspector, he might not be the average one, he might be the lower one, and then the confidence bounds are not valid for that anymore. So when you do this, be sure to use this for inspectors or results that are consistent. Also, yeah, sorry. Also, please note that the maximum likelihood POD is much higher. So as it was for the 29 out of 29, we still have the same issue here that we need to have a knockdown. We need to have, you need to be better, significantly better than the 90% that we say to prove the 95% confidence. So usually inspectors need to have about 98% confidence to achieve the 98% probability of detection to achieve the 90% probability of detection with the 95% confidence bound. And also, if you have a large miss, that can be a disaster, even if it's a single miss. So here we have two curves. This one here is because of this one single big miss here, which violates all the assumptions that we have. Bigger cracks should be easier to find, but somehow we missed this one. And this actually happens sometimes. Every inspector thinks it doesn't happen for him, but it does happen every now and then. And if we take this away, then we have the blue curves. And so even a single big miss is a disaster. So we have two methodologies. Which one should we use then? Well, the A hat versus A is sensitive to reporting. So if it's not automated, it's probably not a good choice. It also cannot give credit to small hits. People can actually find cracks with very low signal to noise ratios, but the A hat versus A cannot take credit for that. Also, and conversely, the A hat versus A implicitly assumes that you will find all the big cracks. In actual reality, people miss bigger cracks, even with high signal to noise ratio, and this goes unmissed. So it's really best used in automated inspections. The hit miss has some problems of its own as well. If the data is insufficient in some ways, you can not have good confidence bounds, or you might not have confidence bounds at all, and then you need to re-administer the test with better setup. But the rule of thumb is, if in doubt, use hit and miss. You take credit for more things like human factors and things like this in more consistent manner. So some final notes for my years in POD, what I've learned. There are some things that are unintuitive about NDT reliability, and I want to share that experience that I've had. One of the common questions that I have is, well, if the people find the small cracks, why do they miss the big ones? I mean, you already said that the bigger ones are easier to find. Why do they find the difficult ones and miss the big ones? It's a good question. It does happen. There's many reasons for it, but it's still a good question. There is an aspect of flaw variety. So flaws are natural artifacts, even if they are nominally of same size. Some are more difficult than others, and this causes the variation. There might be systemic problems. Maybe the probes do not fit, and flaws in some locations are missed. And this rarely happens, but when it does happen, it's important to catch this, and it's usually quite easy to correct. So then the POD has been worthwhile. And also there is human inconsistency. People get tired, and they also adjust their thresholds based on the data that they've just seen. So this also causes this kind of variability. The most important reason, though, is that when people focus on something, they miss everything around it. And so if people focus on the wrong thing, they tend to miss big cracks. So make sure that you focus on finding the big cracks first. And this leads to what I call the NDT reliability paradox. If you focus too much on finding small cracks, it actually lessens your probability of finding the big cracks, or increases the probability that you miss big cracks and reduces your reliability. So focus on finding the big cracks first. And finding the small flaws is nice, but it's a distant second to finding the big cracks. Also, making false calls. It's sometimes assumed that if you look very carefully, you tend to make a lot of false calls, but then you also increase your POD. And this has some grounds in the A hat versus A. But for human inspections, there is really no correlation. Sometimes there is a poor correlation, but usually no correlation at all. And the reason for this is that people make false calls on the limit of what they can detect. So when they try to find the smallest possible flaws, they make false calls. But the smallest flaws that you find are not really important regarding the reliability of the whole system. What is important is missing the big ones. And you don't really make the false calls on the big cracks. And because of that, false call rate usually has a very poor correlation with POD. So don't try to be very careful and make a lot of false calls and think you're better. It usually doesn't follow. Experience also is not a guarantee. Usually people do not see what they miss, and because of that, it's very difficult for NDT inspectors to learn to be more reliable. So we've constantly seen that people who are very new to this job, but perform consistently and have a good focus, can have very good results, as good as any of the inspectors that have been on the job for 20 years. And sometimes we see that the people who have been in the job for 20 years are becoming complacent. They haven't really seen what they've missed, so that they think that they never miss anything, and they can be careless and they can have bad results. So if you're new to the job, don't worry, be consistent, mind your focus, and you should be okay. If you're very experienced, be mindful. It's a bit different experience, use it well. And finally, there's the cost of reliability. POD is not very highly used because it used to be prohibitingly expensive. There is a rule of thumb saying that in the old days, POD used to cost about 200,000 euros, and that's too much for most inspection companies. It's only used in aerospace applications, and even then in equipment, original equipment manufacturers, and so on. But this is no longer the case. There's new developments, and POD is now much more affordable than what it used to be. There are service companies like Trueflaw or others that can come to your premises with briefcase full of cracks and have a POD exercise at your location at the cost of several thousand euros, which is very affordable. Or if this is not possible for your inspection method, if you need to have real components and things like this, we now have virtual flaws and other ways to do it. So it's very much underused because people think it's too difficult and too expensive, and it used to be, but this is no longer the case. So, think again and ask some quotes if you think about this. It's much more affordable than you would think. So, to conclude, unreliable NDT is useless or worse. So reliability is paramount. And if you want to develop your system to be more reliable, you do need to measure it. Otherwise, you might be fooling yourself and doing something counterproductive. And the best way to do this is with the hit-miss POD, where you actually work with the data given to you by the. And that's it for me.